what happens? We got that bottom section. What would you look for an addition reaction? What was that? All right, so what we're looking at doing is increasing the number of sigma bonds. So we will have 2 new sigma bonds. How did we get those new sigma bonds? Primary thing is we're looking at is we're starting with a pi bond. Okay? And in particular, this pi bond, how would you describe it? What type of pi bond is that? I know, it's a vague question. See what you come up with. We are looking at a non-polar pi bond. Why is it non-polar? We're looking at carbon and carbon. Okay? The electronegativities are identical between those two, so we have a non-polar pi bond. Okay? No net dipole. Okay? The dipole, or our polar pi bonds, is a whole other section. That shows up in second semester, so we don't have to worry about it now. So what we're starting with is this alkene, and somehow we are now adding 2 new sigma bonds to this. Okay, so that's our dynamic behind this. If one of those sigma bonds happens to be to a hydrogen that came from H+, then what did the alkene act as? The alkene was a base. If that new bond was instead formed from some other atom that was positively charged, our alkene acted as a nucleophile. You'll notice that the alkene does not act as an electrophile. Why might it not act as an electrophile? What's the reactivity of the alkene? What makes this structure unstable? The pi bond, the electrons in the pi bond. Why are those electrons more unstable than anything else in that structure? They're higher energy electrons. Those are the electrons that are involved in the reaction. We now have a source of electrons. Okay? Can a source of electrons act as an electrophile?
No.
That gets a little bit weird, okay? Which we will see in chapter 12, but it gets a little bit weird. Okay? So when we're looking at our alkenes, they are primarily nucleophilic carbons, or they are Bronsted basic carbons. We can look at our structures. We've got that pi bond. What is special about that pi bond? Can I rotate? No, I am locked in that conformation. Okay. Could that be important when we look at the product? Yeah, because that's going to potentially force certain stereochemistries depending on how the reaction worked. Other things to be aware of. We can look at degrees of unsaturation. A single pi bond is a degree of unsaturation. So we might be asked to go through and run through a bunch of calculations to figure out the degrees of unsaturation for our compound. So we've got that formula floating back into our problem. The other thing, because that rotation, we don't have that rotation, we have cis-trans isomerism. How do we identify that when we look at our structure? Well, we could go through and follow the rules that we talked about way earlier in the beginning of the semester. Okay, but cutting our double bond perpendicular to the pi bond, starring our highest priorities. Okay, and then cutting parallel and looking where those stars were. Okay. If we have those stars on opposite sides, then we've got trans. We have the stars on the same side, cis. So depending on what we're referencing, if we're really only looking at the location of 2 individual groups, we got cis and trans. If we're looking at naming our compound, cis and trans is a horrible way to name because it really officially only applies to the relationship between 2 structures or 2 substituents. So our official nomenclature goes back to the Z and E nomenclature system. So we've got all our nomenclature rules. Of course, you've got all memorized by now, right? Of course, yeah, that's a good answer. Okay, so let's test it. We got some problems to work. Where'd you all start with this? I would argue you should start down here. Why should you start at the bottom? You're timed. Don't work on the hardest problem first. Okay, that bottom one is quite likely easier than the top one. Okay, you're looking at alkenes versus alkynes. Okay, only one type of double bond. And we may find out later that it's not the easiest. That's fine. Okay, but try and get some pieces down on all of these. So minimally, what you should have written down. 1, 2, 3, 4. We got hex. We've got ene. I got 2 enes, so I'm going to go hex-diene. Because it's symmetrical. 1, 2, 3, 4, 5, 6. I'd get the same numbers. I would minimally write 2, 4. Hex-diene. Would have noticed in my multiple choice that I probably need a hexa-diene. Would I have the answer right? Anybody do this one? Is this answer right? Technically wrong. We'll come back to it in a second. Which one should you try now? A lot of people said the first one, so let's take a swing at the first one. How many carbons? So immediately pent, or pet, depending on how you like to spell. We got pent, we have an alkyne, we've got a chloro. We've got all sorts of numbering that has to come in with this, but at least we've got a basic skeleton to work around. Okay. Work on getting the bulk information down, then you can worry about the details later. What are those details going to be in this case? Numbering. Which way do you number it? Left to right, right to left? Left to right, alkynes take precedence. Which means our alkyne shows up at what position? 1, so we could include the one closest to that. Doesn't really matter if we include it there or in front of the pent, which then means our chloro shows up at our 5 position. Turns out that one was actually pretty straightforward. Okay. Which one should you try now? Ring. Okay. I heard a lot of you saying ring, and I heard one person say probably the more important word, not ring, but cyclo. Okay. So when you see that ring, you need to be thinking cyclo. Okay. You've got to focus on connecting ring to cyclo. Don't make everything cyclic, because not everything is cyclic. Okay. So we now have cyclo. What other information could we add to this? Could go through and drop in the methyl. I'm okay with that. I heard people reference the ene. We could throw that in there. How many carbons? 1, 2, 3, 4, 5, 6, 7. I've got 7 carbons, so I've got a cyclohept. Okay. What's the primary functional group within the structure? An alkene. We now have, again, the makings of our overall structure. The details being numbering. How do we number? We start at the pi bond. Which carbon of the pi bond? Why do we pick the left one? That puts the lowest numbering on the methyl. Our pi bond is by definition going to be within our lowest numbers within a cyclic structure. It's always going to be 1, 2. Okay? That's how the numbering system must go, which means we have a 3-methyl cycloheptene. We could probably even get away with just calling it cycloheptene. We don't need to specify the 1. You might see it pop up just in case. Okay? What if you were given 2 options, 3-methyl cyclohept 1-ene and 3-methylcycloheptene. Get rid of the 1. Okay? It's not necessary within the name, so you actually ditch the 1. It's kind of a weird system. Okay?
Question about when you add the letters like O and P.
So O, M, and P show up on aromatic structures and officially on benzene. How many carbons are in benzene? 6 carbons with 3 double bonds. We do not have benzene. So you do not need to use O, M, and P. O, M, and P are actually technically not the most appropriate way to name. You should be naming with the numbers.
Right.
Yeah.
That's my question.
Top one, variety of ways that we could have counted carbons. Heard one option was going through our purple line here, and that gets us 5 carbons. But that excludes the OH from the main chain. The alcohol is our highest priority functional group. It must be included in the main chain. So we're looking at 4 carbons, which means bute. We have an alcohol, which means we have an alkene, which means and we also have these chloros and so a couple names. Isopropyl, absolutely a valid name to use, though you probably wouldn't see it on the ACS. You would instead see 1-methyl-ethyl. Both of those are valid nomenclature systems for that. Okay. That 1 references this carbon. It does not reference the carbon of our main chain. So now we got to put it all together. It's going to require figuring out all our numbers and our priorities. Where should we start numbering? Left to right, right to left? Right to left because alcohol being our highest priority. Where's the alkene? Position 2. We've got 2 chloros, so we can call it dichloro. Where are those chloros located? 3 and 4. And then we also have our isopropyl, or our 1-methyl-ethyl, which showed up where? Position 2. Okay. You'll notice that I did not put this in any particular alphabetical order. Why not? Because I always get confused by the alphabetical order, so I hope I don't have to worry about it. Okay. Typically, you don't. Okay. Which one comes first? Dichloro or isopropyl? Pretty much any way you look at it. Your chloro officially comes first. Okay. So it's the C of the dichloro that puts it out front, in front of what? So we could try and jump to the IUPAC name, either the M of our methyl or P of our isopropyl. Okay. Either way, we've got our name mostly put together. What's the mostly issue? We have a cis-trans isomer. So I'm going to erase everything. When assigning our cis-trans system, what we do is we cut perpendicular, star, star. Why did I star those two? On each of their halves, they are the highest priority. Chlorine versus carbon, chlorine's higher priority. On the other half, carbon versus carbon, no difference, so we go out. Oxygen versus carbon, oxygen takes priority. So those two are our priority. We cut now parallel to the double bond. Where are our stars? On the same side, which makes them cis, which makes them Z. for being on the same side. Okay? Since we added that increased complication, let's go through and add it again on our bottom one. What's the issue we encounter here? I'm going to run into the same deal. Both of them exhibit cis-trans isomerism. One is trans, which means E, and the other one is cis, which means Z. Which brings up the next interesting question. You all remember what the name was? Which one is E? Which one is Z? Anybody notice a problem with this? You can number it either direction and still get to the answer. Okay? This was a random question I happened to put together, and some student was smart alecky enough to then ask the question, well, which one belongs where? It's a really good question. Okay? One that I had no clue on. So I went online, checked the book, checked all sorts of other things, couldn't find it. And the only place I found it was by going all the way back to the actual IUPAC rules in section 2, subsection 3 of naming alkenes. Z is named over E. Okay? So, will you ever encounter the situation where you have to organize that appropriately? Probably not. But hey, it showed up. If I have to do it, might as well make you go through and see it. Okay? So when it comes to nomenclature, there is a rule. It has been defined. It has been created. Whether or not you know that rule is a separate issue. This is why I don't try and name the whole compound from the get-out. I name each of the pieces and hope for the best. Okay? Because the best, 9 times out of 10, is there. I got my answer and I can move on without having to have memorized some useless rule of 2.2.3. Yeah.
If instead of saying isopropyl you did 1-methyl ethyl, how would you number it?
You still, it's the order that mattered there, not the numbering.
Well, it would be 2.
I think I see what you're saying. Never mind.
2-1-methyl ethyl.
Yes. So that substituent would be 2 dash with your parentheses, 1-methyl ethyl. Very often you'll notice that that 1 is dropped from it. Okay? And in some cases you can even see the parentheses dropped from it, which makes it even more misleading. Okay? So just kind of watch out for that. Really rare, but it does show up. Questions? Nomenclature. Practice it. I am in the process, well, I built one nomenclature assignment that had all of the nomenclature that we've done throughout the entire semester in one giant assignment. Turns out that giant assignment, thanks to some people pointing out the potentially obvious that I had not even thought of, is way too ginormous and is a little cumbersome to deal with. I'm in the process of cutting it down. Okay? So right now I believe I have a chapter 1 pool and a chapter 2 pool of all of the possible questions that SmartWork has put together on nomenclature. So if you need practice on nomenclature, just go in and start working problems. Each of those sections should be about 30 questions apiece. So this is the next fun part. What you're seeing up here is what I like to refer to, or is commonly referred to, as a spider diagram. What this spider diagram shows is all of the alkene addition reactions that you are ultimately going to be held responsible for. All of these we are going to talk about in the next 3 weeks, really 2.5 weeks. So as a quick subdivide to make it look a little bit less insane, and like I said, it's only a little bit less insane. This section is chapter 11. This guy right here is chapter 25. And everything else, chapter 12. Okay. If you haven't seen this before, now's a good time to look at it. Start to memorize this. You are responsible for these reagents. Okay, the addition reactions is the first case where now you have reagents that you have to know and what they do and how they work. Okay? There's a lot of information embedded within this. Okay? For instance, we take a look at this reaction. Our alkene plus bromine goes to our product. What's that extra information that's embedded there? There's an enantiomer associated with this. Okay? Kind of unfortunate because that should have been included nearly around the whole thing. There's something else that's embedded within that.
The stereochemistry.
Wedge dash. How the groups are added across the double bond is embedded in this. That information is available to you. Right? So that tells you something about how the reaction worked, the mechanism behind it. If you understand the mechanism, the result makes perfect sense. If you don't understand the mechanism, then what you have to do is memorize the result, but not for that reaction, for every single one of these. That gets tedious fast. That's why you need to understand how these things work. And that's how we've been approaching all of our reactions. Find our negatives, find our positives, do the reaction. What are the repercussions of that single reaction? How could this potentially continue forwards? Okay? So, there's a big, again, depressing thing to look at. So now let's move on into our addition reaction. Okay? So if we take a look, we've got our overall reaction kind of drawn above. Okay, we have our alkene reacting with a Lewis acid and a Lewis base. The result is that the Lewis acid connects and our Lewis base connects. And I tried to color code that, which you may or may not be able to see. Our pi bond, shown in red, hooks up with what?
The Lewis base.
It's the Lewis acid it hooks up with. Why would it hook up with the Lewis acid? Lewis acids, by definition, accept electrons. So by highlighting the pi bond in that color, we've now identified something as an electron donor. It's going to donate those electrons to our Lewis acid. What happens with our Lewis base? Well, the Lewis base was originally connected to our Lewis acid. Where did those electrons then go? Goes to the other position on our alkene. Why would they go to the other position? Some of you are propagating it out and seeing the result. What's the resonance structure for this guy? Let's take those electrons and let's move them to this carbon. What charge does that carbon become? For it to become negative, what happened to the other carbon? It became positive. We find negative, we find positive, what do? We put them together. There it is, there's our product, there's our reaction addition done. Okay? How it occurs is ultimately what Chapter 11 and Chapter 12 are looking at. In Chapter 11, we're not reacting with now a Lewis acid, or we're reacting still with a Lewis acid, but we're taking it a step further and we're classifying it as a Bronsted-Lowry acid. Okay? When we move to Chapter 12, our initial step is now going to be with an electrophile. Okay? Not the general term of our Lewis acid, and most certainly not a Bronsted-Lowry acid. So we can see the end results in each of those experiments. Sometimes they are required to go through a whole bunch of extra steps. Chapter 12 has a lot of extra steps. That's partly why we'll go through and spend some time there. Right? So, anybody notice anything else interesting about where I drew the Lewis acid, where I drew the Lewis base? Yeah, this structure is not symmetrical. You'll notice that we have that R group sitting out there. Why did I not draw the other result? Okay, what would that other result have looked like? That other result would have been Lewis acid, Lewis base. Interesting. I didn't say there were two products. I said there was only one. Why did I not show this other product? If I rotate about the sigma bond, the Lewis acid is still connected to the carbon with the R group in that new product. That is not the case in the one that was drawn. Why is this product not formed?
It's a carbocation that you would have formed, but it's less stable.
What you need to do is evaluate your alkene, and in particular, the resonance, possible resonance structures of our alkene. If we look at the alkene resonance structure that we drew, that is a valid resonance structure. Is there another? Yeah. What's that other resonance structure look like?
Negative on the left.
Same, but the charges are flipped. As Jimmy was alluding to, what's the big difference between those? The location of the carbocation. In the first structure drawn, our carbocation is located on what kind of carbon? Secondary. It's a hydrogen. And the initial one, or the last one drawn, it becomes primary. Which one stabilizes the positive charge better? The secondary. What ends up happening? We only see the secondary dominating the result of this, which means all of the chemistry is coming from understanding the resonance structures and evaluating the stability of each of those structures. Both the chemistry in Chapter 11 and Chapter 12 are following that exact same route. There is no difference between them. Right? You are evaluating the stability of that intermediate, that resonance structure. All of the chemistry that is predicted afterwards comes from that. Okay, so take a crack at it. Okay, let's start it up. How's the mechanism start? We could try and draw resonance to help us figure it out. There's one option. Both of you guys are suggesting the same thing. We could try and start immediately moving pi electrons. Drawing out the resonance would be helpful to decide which atom is most likely to be negative, which atom is most likely to be positive. If we look at the resonance structures for this compound, what do we find? They're the same. Do we need to worry about that whole arrangement of where the atoms go? No. Okay? So we were kind of nice at first because it doesn't matter. How many bonds does the hydrogen now have? Too many bonds. What do we have to do? Break a bond. What's the result? We now have a carbocation. The hydrogen went into our structure. Because we can imply hydrogens, we don't even have to show it. Now what happens? The bromide, negative bromide, attacks the positive carbocation, and we end up with our result. You notice I made it look like I drew the bromine attached to a different carbon. Is it a different carbon? No. Remember, this molecule is symmetric. Doesn't matter which way we draw this. So we have our overall mechanism nicely drawn out for us. So now what we want to do is shuttle this into an energy diagram. Okay, I said even if you didn't know the mechanism, you should start to be able to come up with an energy diagram. Right? What are the 2 points I would expect you to be able to place? The reactant and our product. So let's say the reactant, because we don't really know much about it yet, somewhere in the middle. Where should we place the product? Why should the product be lower than it? Why is it lower in energy? No pi bond. Fantastic. Good job, guys. We've got our product somewhere lower in energy than it. Okay. This is something that's characteristic for our addition reactions. They are all almost always exothermic because you're starting at a pi bond and ending at sigma. Sigma is lower than pi. Okay. If that was all we had, then we've at least got something down, we can move on. Okay? But since we have the mechanism now, we have to draw in our intermediate. Where should that intermediate show up? Should be higher in energy than both of those. Why? It's charged. So there's my intermediate. Oh, it's going to look lovely. Okay. Now what do I do to connect them? Cool, there we go. We now have an energy diagram that we can deal with. Okay? That energy diagram is something that you should be kind of internalizing and looking at the relative stability of each of your products as you draw them out and saying, what's the relationship? Is this exothermic? Is this endothermic? A large part of this chapter, right at the tail end, is going to get to evaluating our energy diagram in terms of kinetics and thermodynamics. Because addition reactions can have two possible products, a kinetic product and a thermodynamic product. Okay, so it's a tricky aspect that's coming out of evaluating how a reaction works. So, what happens with our unsymmetric alkenes? So we got three reactions here. Okay. In the three reactions shown, what is common? Assuming I did it right. Yes, cool. They are all addition reactions. What else? What's that? Okay, so we used a halogen as a nucleophile, so we can also refer to these as hydrohalogenation reactions. In fact, a hydrohalogenation addition reaction, because we've got the addition there, we've added a halide, and the hydro in this case is in reference to the hydrogen being added. So they are all hydrohalogenation addition reactions. What else is common? So they're all strong acids. So in the hydrohalogenation reaction, hydrohalogen, there are strong acids. Okay? So that is also valid. What else is valid? There's no stereochemistry shown in these. Okay? We do have, well, we don't have cis-trans isomerism in all of those. We only have it for one, actually. What's that? Speak up, Patricia.
They all use vocabulary.
Okay. Our new hydrogen seems to go to the position that is always the least substituted. Our halogen always goes to the most substituted position. All three of these reactions get the exact same result. Okay. Hydrogen goes to the least substituted position. Said another way, the hydrogen that is being added to our double bond goes to the position that already has the most hydrogens. This observation was made, I don't know when, a while ago. Okay. And in that observation, they really didn't have any other understanding of what was going on within the mechanism or the reactivity of it. They just noticed that where the hydrogen was located. So of course they invented a rule. Okay? That rule is that when we're doing these hydrohalogenation addition reactions, the hydrogen will always go to the position that has the most hydrogen. Okay? And I know you're all frantically writing that down. It's a horrible, stupid rule. Okay? It's an observational rule that makes very little sense based on the chemistry that's going on with this. Okay? But because of the history associated with this discovery, everybody then references these types of reactions according to that guy's name. His name was Markovnikov. Okay? So before we actually had an understanding of the mechanism or potentially how molecules even reacted, all we saw is where hydrogens go. Hydrogen adds to the carbon that has the most hydrogen. Okay? The phrase that typically comes out of this is the rich get richer. It's a great mnemonic device for a useless rule. Okay? So don't focus on the rule, focus on the chemistry. What's the chemistry that is similar in all of these situations? The most stable resonance structure is going to put the positive charge where? This one. What are we actually evaluating with this rule? You are looking at the stability of the carbocation intermediate. That's what drives this chemistry, not this Markovnikov or, as you'll soon find later, anti-Markovnikov. Okay? Both the Markovnikov and the anti-Markovnikov classification of reactions go back to the exact same rule, which is all about the stability of the carbocation intermediate. We just end up seeing odd results out of it because we don't always react with a positive hydrogen. We could react with a negative hydrogen. Oh, but now it's a negative hydrogen. We come up with a whole new rule. That's a load of crap. It's not. It goes back to the stability of the intermediates. Focus on the stability of the structures. The rule is an arbitrary name. Okay? So if we go through and look at these two reactions, okay, we've got two possible systems coming out of this. Okay? In our top case, we're showing the hydrogen, okay, going to the position that already has the most hydrogens, which puts the carbocation on the tertiary. Okay? We get our product out of it that we would expect. The other result is the hydrogen goes to the other carbon, which puts our carbocation on the secondary position. So the chloride comes in. How do we interpret this information in the energy diagram? Well, where's our alkene energy for both these reactions? In the exact same space. Let's go ahead and put it right here. There's our alkene. Where's the intermediate for the red hydrogen? So this top reaction. Okay, it should be above the reactant energy. Absolutely agree. Where should its product be? Below the reactant. Okay, so we could go through and look at this reaction. Right? What happens with our bottom case?
The intermediate higher.
Why is the intermediate higher in energy?
Because it's less stable.
Why is it less stable?
Because it's secondary.
The secondary carbocation is less stable, which means it's higher in energy. Okay. Yes?
Does the intermediate always form, so to speak, or does it ever happen like a SN2 at all?
With this type of reaction, with our hydrohalogenations, we always form that intermediate. Okay. Can we change that? Absolutely. Let's worry about that in chapter 12. Okay. When we're adding a strong acid, our primary focus is stabilizing the positive hydrogen. That's where all the chemistry sits. Okay. The rest of it is a secondary step. Okay. So we end up forming a carbocation in the process of neutralizing that strong acid. Now that we have that carbocation, what can we do with it after the fact? That's where the rest of this chemistry comes in. So if we go through and take a look at this very first step, which product would we expect to form? The red one or the blue one?
Which product?
Okay. So we notice I haven't actually drawn the product for the blue one yet. Which product, based on these curves that you're seeing, which one of these would you expect to make it to the product? Red or blue? Why the red one? It forms faster. Kinetically, that one makes sense. Our intermediate happens a lot quicker. So we have a kinetic product here because it's happening faster. Okay. This is a confusion that popped up with the SN1 reaction. We talked about cation stability. And we said the tertiary carbocation was the most stable. Okay? And we run an SN1 reaction. We end up proving that the tertiary cation was the most stable because our tertiary halides reacted the fastest. That seems counterintuitive. If our tertiary alkyl halide is more stable, why would it react faster?
Because it forms faster.
It's not reacting faster. It's forming the carbocation. Okay? That carbocation is more stable, so it can form. Once it forms, that reaction can occur. Okay? You're looking at the energy diagram, not just raw energies of each of these structures. This brings us to the next question. Where do I draw the product of the blue line?
The same place as the product is present.
We might expect to draw it at the same place as our product because both of them got rid of the alkene, both of them put on a chloride. There's a slight variation, and now we need to start looking and thinking about this variation. What is the most reactive thing in both of those products? The chlorine. Okay. What does that chlorine have a lot around it? What does it have a lot of around it? Electrons. What is going to make that chlorine more reactive? Being around more electrons. So let's take a look at the carbon where the chlorine is bound. It's connected to what? 2 carbons and how about the other one? What's the difference between carbon and hydrogen? Carbon has more electrons. What is that going to do to the stability of the chloride? It's going to make it less stable, which does what to its energy for our red product? Should be higher in energy. So where should I draw the blue product? A little bit lower in energy. Herein lies the next aspect of this. That difference in energy for this structure is relatively minimal. Very, very small.
Is that compared to the needed energy to form the intermediate?
That ultimately is in a relationship back to the energy for our activation for each of these. So the difference in activation energy is massive in comparison to the difference in energy of our final products. Okay? And that becomes important. Okay? That becomes important because if I now ask you which is more stable as a product, blue or red? Blue. If it is more stable, what would you suggest its likelihood of forming as a product? More likely. And yet, what's the result? It's less likely. And it becomes less likely because the mechanism determines the stability of our intermediates. So what we have to do is evaluate not just the raw energy of reactants and products, but also the energy with respect to our intermediates and how do those intermediates affect our overall reaction. There are cases where the difference at the end is big enough to impact the overall result. This first part where we're looking at our activation energies, we said was a result of speed. What determines speed? It's our fancy way for saying speed as far as chemistry goes. Kinetics. That is the relationship between our reactant and our transition state. What's the difference when we look at just the raw stability of our products? That's now looking at the difference between our reactants versus our products, and we are now looking at thermodynamics. I can't spell thermodynamics. Right? So, kinetically, what product do we expect? Red, because faster reaction, shorter activation barrier. Which product is thermodynamically favored? The blue product is our thermodynamic product. It turns out that under most conditions, that difference is so small that what we evaluate is the stability of our intermediate. This is where Markovnikov's kind of backhanded observation was turned into a rule. Right? Didn't understand anything of what was going on the mechanism, he just noticed that where the hydrogen was located. Right? If we evaluate the stability of our intermediates, we will very likely find our answer more quickly and efficiently than memorizing a stupid rule. Please look at the mechanism. Questions? So, we are going to turn this into a 2-minute quiz.